Hi, I'm Sam. I've been doing various forms of Bayesian analysis for years now, mostly in studies of the comparative efficacy of medicines. I've decided to do this presentation because we've reached the stage where software tools and processing power mean applying simple Bayesian statistical analysis should be nearly as accessible as using frequentist statistics. In some situations, it might actually be easier and more intuitive to develop a Bayesian estimate than to try and shoehorn your analysis into a standard frequentist method. I think that's particularly true when we're trying to come up with estimates for everyday life, where it's not a formal statistical analysis, but we're just looking at a problem and trying to break it down. All of this means it's worth having a basic understanding of the fundamentals of Bayesian stuff. If you don't know what I mean by Bayesian or frequentist, don't worry, this presentation is for you. It's for anyone who has a rudimentary knowledge of what stats is and wants to be able to understand what people are talking about when they discuss Bayesian stuff. It's not going to make you suddenly able to do complex Bayesian analysis, but it should help you to understand what people are talking about. Essentially, I want to get people thinking about Bayesian methods, and I want to help you get past the "and then some stats magic happened" bit in papers and reports, where you end up just kind of assuming the analysis was fine because it's so full of jargon and equations. And that happens even if you have quite a decent experience in statistics sometimes. If you find this interesting and useful, I may do a simple practical session to illustrate some of the principles. Let me know if that's the case. But let's get started with this for now. So here's what we're going to go through in this session. We're going to start with a little taster on Bayesian statistics to help you get an idea of why we're doing this. Then I'll introduce some fundamental concepts in statistics. I'll be using these to help you understand conditional probability, which is the probability of one thing happening given some other thing. Using that, we'll then introduce epistemic probability, which moves from the idea of chance to the idea of what you should rationally believe. We'll use the conditional probability stuff to prove Bayes' theorem, which underlies Bayesian statistics, and then we'll talk about applied Bayesian statistics a little bit. Some of this session will involve working stuff out yourself. That's to help you absorb the information efficiently. Obviously you don't have to do it, but it might help to have a pen and paper handy. Some of this does require some mental gymnastics, which may feel a bit difficult depending on whether you're used to thinking in terms of sets of events or things like that, and whether you're used to using set notation and that sort of thing. Just take your time over those bits if you need to. You can pause it at any time. Genuinely, I taught myself about Bayesian fundamentals by doing this work by hand. All the stuff you're doing today is what I did myself to sort of teach myself about Bayesian stuff. It was quite tricky, but I found it a lot easier than passively reading things, and particularly because things like statistical textbooks tend to assume quite a lot of pre-knowledge, but also they tend to approach things in a very equation-heavy way. If the idea of working it out yourself is something that appeals to you, definitely use a pen and paper. Anyway, there's a lot to cover, so let's start with something you can get your teeth into: why Bayes matters. Bayesian statistics matters because we need to make decisions without all the information. Uncertainty matters, and it is vanishingly rare that the research evidence tells us precisely what we want to know. Those of us who make our living out of evidence-based medicine and things know that only too well. You very frequently have a number of trials, but you very rarely find that those trials are in the exact patient group that you're interested in, or they use the exact comparisons that you're interested in. So we need to deal with some of that uncertainty. Bayesian statistics allows us to synthesize what we think we know and what we observe to see how we should change our beliefs as more information becomes available. One thing Bayesian methods do particularly well is allow you to separate out your prior beliefs, your statistical model, and your observations, so that where you have uncertainty, you can understand where that uncertainty is coming from. Bayesian statistics is something you're going to see creeping into a lot of current topics. In medical research, it's a key component in many approaches to network meta-analysis, which is kind of old hat now, but it's also used in things like machine learning and artificial intelligence, and is an important part of that general hum around the large data sets from medical insurance databases, advertising data, etc., etc. In this session, I'm going to run through what Bayesian statistics is in very basic terms. I'm going to use that basic understanding to help you work out when it might be useful. Okay, I've used some horrible buzzwords there and a little bit of jargon. I think a concrete example would help. I know coronavirus is a hot topic at the moment, but it won't be eventually, and I don't want people to overinterpret what I'm talking about. So here's a different question. Do I have Martian earlobe syndrome? Luckily for me, a new test has recently come out for Martian earlobe syndrome that I'm told is 95% sensitive and 99.6% specific. What does that mean? Well, it means this. The sensitivity means that if I have Martian earlobe syndrome, there's a 95% chance that the test will detect it, leaving a 5% chance that it won't. The specificity means that if I don't have Martian earlobe syndrome, there's a 99.6% chance that I'll get a negative result and a 0.4% chance that I'll get a false positive. Cool. So if I get a test and it comes back positive, there's a 95% chance I've got Martian earlobe syndrome, right? Wrong. This is really important. Medical tests are an example of contingent probability, which we'll discuss properly in a bit. For now, you can understand why this is wrong using a couple of Venn diagrams. We're going to be using these a lot. So here we have two populations. Manchester has had a major outbreak of Martian earlobe syndrome, and 75% of the population is affected. So far, Coventry hasn't been affected as badly, but it is starting, and 2% of the population are infected. Now, Manchester starts a testing program to identify and treat patients. Using our test, I can take those colour bars here, so the 75% that are ill and the 25% that aren't, and for each of those I can say if we tested everyone, this is what the results would look like. In Manchester, if you test positive, there's a 99.9% chance that you have Martian earlobe syndrome. Now that's going to mean that the testing program is very popular, but public health officials get worried about disease containment and decide to start rolling the tests out nationally. So the program rolls out to Coventry. In Coventry, the positive test results look like this. In Coventry, if you test positive, there is an 83% chance that you have Martian earlobe syndrome. That means there's nearly a 20% chance that you don't. If you look at these diagrams, you can see why. The rate of illness is really low in Coventry, or relatively low in Coventry. So the number of positive tests overall is small. This sort of orange area is small, a lot smaller than it is in Manchester. And the proportion of people who could get a false positive result is much larger. So anyone you get from the population is far more likely to not have illness in Coventry. The test is still a good test, but its value is changed. It's changed by this thing that we call the base rate, the rate of that illness in the population. If treating Martian earlobe syndrome involved chopping off your ears, you might start to think carefully about whether you want to do that if you're in Coventry. This illustrates the importance of considering those base rates in statistics, and as you'll see later, introduces the idea of contingent probability. But it doesn't tell us about Bayesian statistics quite yet. To get Bayesian, we need to go uncertain. In the real world, we only know how common an illness is in an area because of testing. When we start testing, we don't know what the prevalence is, so we can't really estimate the risk of a false positive. There may also be uncertainty about the sensitivity and specificity of the test itself. More fundamentally though, your individual risk, and we're often talking about making individual decisions, your individual risk is not the same as the risk of the population overall. You may be someone who never goes out, you may never expose yourself to risk, or you may be somebody who has to go out for work and shopping quite a lot and so expose yourself to ill people. The secret trick of Bayesian analysis is that it gives us a way of handling that uncertainty, of deciding amongst all the bits of uncertainty in a decision which bits matter most. This then helps us to see how to reduce uncertainty. Bayesianism is all about supporting decisions by accepting uncertainty. It fits really nicely with decision analytic models, methods like modelling, and other approaches to understanding human decision making. We're going to return to Martian earlobe syndrome during the session, and you'll work out for yourself whether you have it and how uncertain you should be about that. But of course, Bayesianism isn't just about earlobes and made-up diseases. The ability to model decision making under uncertainty means that we can apply it to lots of situations. Here are some examples. So we've got indirect treatment comparisons and network meta-analysis, which is the sort of thing that I've done quite a bit of. We've also got testing and disease modelling that I have some experience of. But then you've got everyday stuff like email spam detection, character recognition programs when you're trying to read images to pull out text. Then you've got some more sort of ninja stuff like some of the facial recognition algorithms, climate change and geostatistics where we're dealing with really large complex systems, and reasoning engines. Let's not get ahead of ourselves though, let's go right back to the beginning. To understand Bayesian statistics, it's useful to understand some basic ideas in all statistics. I mean, it's pretty useful for life generally, in fact, so no apologies for covering this stuff. That subtitle will become clear in a bit. If we start with probability, we can think of probability in two ways. We have chance and we have judgment. Not everyone's going to split it up precisely like this, but it works for us. Chance has served really well in statistics for a long time. The chance-based idea of probability starts with engineered games of chance. It then uses those as models of things we observe in nature. Chance-based probability is powerful enough to give us things like the normal distribution, regression models, and most of the data analytic tools we use today. Even a lot of things which are called artificial intelligence or machine learning are really nothing more than quite straightforward regression models. Most of the statistics we're taught, if we've done a statistics course at school or university, is based around chance. There's a very good reason to this. We can control everything that happens in a game of chance. Through the rules of the game, we can set probabilities that we can test and we can prove. We can then go out and play the game and show that they match what we expect. The other, perhaps more subtle reason that we've concentrated on games of chance in the past is that a lot of the burgeoning of research in statistics happened in the 17th century or even earlier, when things like box sets of The Wire and What We Do in the Shadows weren't available, and people played cards instead. Indeed, one of the earliest European investigators into probability, somebody called Cardano, actually made a proportion of his income from gambling. So there's a bias that comes from that. If we then move on to judgment-based ideas of probability here on the right, judgment-based ideas of probability feel simultaneously a lot more woolly and difficult, but also more reflective of the real world. Overall, wouldn't it be nice to have the concrete manageability of chance alongside the practical utility of judgment-based approaches? Well, that's what Bayesianism does, really. But I'm getting ahead of myself. Just like those early investigators, we're going to start with probability based around chance, and I'll show you how that leads to judgment-based probability. So we're going to call this analytic probability because that's what it's called. If I choose a card at random from a deck, what's the chance that it's an ace of spades? Well, that's a pretty easy problem. There's only one ace of spades in a standard deck of cards, and there are 52 cards in a standard deck if we exclude the jokers. Therefore, the answer is 1 over 52, or 0.019. In analytic probability, we just look at the number of ways an outcome could occur, and then we divide it by all the possible outcomes. There are some nuances to that, but that's essentially all we're doing. Analytic probability, expressed this way, is useful because it forces us to think of problems carefully. However, it quickly becomes quite cumbersome if we have to work out all the possible outcomes for an event. To illustrate this, what's the chance of me getting the ace of spades if I choose 3 cards randomly from the deck? If you want to work that one out for yourself, pause the video now. Okay. A lot of you will have said 3 out of 52, which is correct, but you'll probably be feeling a little uncomfortable about why it's correct. Here goes. Let's get our equation back first. First, let's look at the number of ways of getting an ace of spades. Well, it could be the first, second, or third card, like so. If it's the first card, there's only one way of doing that. Then there are going to be 51 cards left, any of which could be fine for the second card. And finally, for the third card, there are 50 left, and it could be any of them. That means there are 1 times 51 times 50 ways of doing it. We can do the same with the other ways of getting an ace of spades. So if the ace of spades is the middle card, there are 51 ways that we could choose the first card because we can't choose the ace of spades. Then we choose the ace of spades, there's only one way of doing that, and then there are 50 cards left. And we can do the same with a chance of getting no ace of spades. If we put all those numbers into the basic equation we've got on the left, we get this monster. All of those bits in brackets contain 50 times 51. Just look at the equation for a little bit. So we've got 51 times 50 there, 51 times 50 there, 51 times 50, 51 times 50, 51 times 50, 51 times 50, 51 times 50. So they've all got that in. So that's really cool because it means that we can simplify it. And we can simplify it to this, which is 3 over 52. So 1 plus 1 plus 1, that's 3, 49, 50, 51, 52. So we've demonstrated the answer to that using analytic probability. And the thing which a lot of you will have just come through sort of intuition, it can also be got to using a horribly complicated equation. One way to think about analytic probability, which will make everything else easier, is to use set theory. Here's the set of all possible outcomes of 3 cards being picked from a deck of cards. I know it just looks like a big circle, but it's the set of all possible ways of getting that. Now, we already worked out how many members that set has. 52 times 51 times 50, which is what you'd work out yourself. We also worked out the size of the set with the ace of spades. So that's it. And that gives us a set that looks like this. So we have the set of all possible outcomes, and then we've got the set of the outcomes that include an ace of spades. All of this means that we can express basic analytic probability using set notation. Ah! I can hear you thinking, don't worry. This is just saying that the probability of outcome A is the number of ways that A can occur over the number of possible outcomes. So here it's A union A prime, so that's the number of ways that A can occur plus the number of ways that A doesn't occur. The size of set A and not set A, or A prime, is everything that can happen. We call that the universal set, and it's what the big blue circle captures. Now this may seem unnecessarily complex, and it is for this example, but it's going to help us in a moment. Plus, it introduces the particular approach to set notation that I'll be using, which is why I've done it really. Okay, so far so good. We can use what we've done so far to work out some pretty neat laws. First of all, we can work out the addition law. So the addition law is pretty intuitive once you're thinking of probability in terms of sets. The addition law states that the probability of A or B happening is the probability of A happening plus the probability of B happening minus the probability of them both happening. We can express that using set notation, and a pretty picture is going to help make sense of it. It's kind of obvious really, but it's more obvious when you look at a picture, I think. We know that the size of A and B together, i.e. A union B, is the same as the size of A plus the size of B minus the intersection of the two. Because we don't want to double count it, do we? Because otherwise we'd be counting it when we count A and when we count B. Now there's obviously a special case of this where the size of the overlap between A and B is 0, and we don't need to worry about it. In this case, A and B cannot both happen. So if the size of the overlap is 0, you can't have A and B both happening, and they're considered mutually exclusive. As an example of that, if we toss a coin, we can either get a heads or we can get a tails, but we can't get a heads and a tails. Now the multiplication law is a little bit more tricky, I think, but it's directly relevant to Bayesian statistics. The multiplication law states that the probability of A and B happening is the probability of A happening times the probability of B happening given that A has happened. Whoa. I still find that confusing, and I know what it means. I think this is horribly confusing, but it's actually rather simple when you think it through carefully. It's those P's that make it confusing. So there it is, expressed as set notation. The probability of A and B happening is the probability of A happening multiplied by the probability of B given that A has happened. So let's have a go getting rid of those p's and using n's instead to make more sense. Remember that n can be used to tell us the size of a set. So let's clear some space first. Right, we're interested in the intersection of A and B. That's this little bit here. And there we have A intersection B to label it. Now we already know, because of basic probability stuff, that the probability of A and B occurring is a number of ways A and B can occur, i.e. the number of events in that intersection, in that little bit in the middle, divided by the total number of outcomes possible, which is the blue circle, the universal set. So there it is written in set notation. P A intersection B is number in A intersection B over number in the universal set. We can use the same approach to say that the probability of B occurring, given that A occurs, is the size of the intersection divided by the size of A. There we are, there's the set notation for that. That is the number of events where A and B occur, so this intersection here, divided by the number of sets where A occurs. So that's the number of events where A occurs, which is the size of set A. So you can see the probability of B, given that we know that A has occurred, is going to be that bit divided by that bit. You can think of this as the proportion of A events where B also happens. If that's not immediately obvious, think back to the basics of analytic probability. There's no shame in this being a little bit tricky to get your head around. Okay, we also know that the probability of A is the number of events in the A set divided by all the events that could happen in that universal set. So here we are, probability of A is number in A over number in the universal set, so that's this A set over the whole universal set. Then if we multiply the probability of A by the probability of B given A, we get this weird thing, which is the probability of A and B occurring. So here we are, N, A and B, this bit here, over NU. Yeah, so that's the probability of A and B occurring. It's the same as probability of A occurring multiplied by the probability of B given A. So we've just proved the multiplication law without really intending to. Well, now the multiplication law is very useful for lots of things, but its real value to us comes when we rearrange it to give us a way of describing conditional probability. We're going to do that now. So you may be struggling a little bit at the moment. I've just introduced some statistical concepts which, while basic, involve us thinking about things in quite an abstract way, using weird notations that might be new to you, etc. And each of those things is quite tricky. Abstract thinking is difficult, new notations are difficult. So if you've not quite followed, that's okay. You might want to just go back and look at a couple of the slides again. You may also be asking why on earth I've introduced something that you want to use practically using this abstract approach. The reason is this. If we represent the world using abstract concepts and symbols, we can manipulate them and come up with new insights which might not be immediately obvious. We're going to do that in a second, and then I'll give you a concrete example to help bring it all together. So bear with me. You see this equation that captures the multiplication law? Because we're doing this using abstract symbols, we can rearrange it. We can rearrange it to describe the probability of B happening given that A happens. Watch. So this is a rearrangement of this equation here. This new equation, PB pipe A, describes the probability of B given that A has happened. This is formally described as conditional probability, and a statistician might say it's the probability of B conditional on A. We've got to it in quite a complicated way, but let's look at it using our basic numbers. The number of ways that A and B could happen in that intersection of A and B here. If we know that A has happened already, all the possible things that could happen are inside set A. So set A, this set here, becomes our universal set, if you like, for our bit of work. So that's the denominator, the bit that goes on the bottom in our probability calculation. We've come a long way, but the basic principle is the same as we started with. The probability of an outcome is the number of ways the outcome could occur divided by the number of ways anything could occur. There it is again. The only difference is that we already know A has occurred. So the number of ways any outcome could occur is contained within that set A. Right, now for a little bit of magic. Here on the left are two equations. They're both based on the multiplication law. So we know that they're both true because we've gone to the effort of proving it. But they're different conditional probabilities. So we have the probability of B given A and the probability of A given B. Now they've both got this PA intersection B value in there. And when we see the same thing in different equations, we know we can do some funky manipulation. And in this case, that means we can do a little bit of algebra to create a new equation. So we take that intersect. We know that it's P, BA, PA. So we take that from here by rearranging that. And then we can substitute that value into the PA given B equation. We come up with this, which looks complicated, doesn't it? This new equation is Bayes' theorem. And while it looks complicated, because it is, it's pretty powerful. You'll see why now. So I promised you a concrete example. So let's return to our question about Martian earlobe syndrome. Right, we're back with Martian earlobe syndrome. I told you right at the beginning that we'd work out how to use Bayesian approaches to solve the problem of how to interpret a positive Martian earlobe syndrome test. We're going to do the first step of that now. Here's the table that told us about the reliability of the Martian earlobe syndrome test. And here's Bayes' theorem. In our case, A there is having Martian earlobe syndrome, and B is a positive test. So let's fill in the equation with meaningful things. So here we have the probability of having Martian earlobe syndrome given a positive test equals this lot here. Now pretty quickly you can see that we have one of the parameters in the equation. Our table tells us that if we have Martian earlobe syndrome, the chance of a positive test is 95%. So probability of a positive test given that we have Martian earlobe syndrome is 95%. So we can put it in here. Let's make a note of that. The probability that we have Martian earlobe syndrome is the thing we don't know, so we'll leave that for now. That leaves the probability that we get a positive test, this bit at the bottom. That's quite a complicated thing to think of. However, we know that we either have Martian earlobe syndrome or we don't. And we know that the chance of getting a positive test if we do have Martian earlobe syndrome. You may also have realised that we know the chance of getting a positive test if we don't have Martian earlobe syndrome. It's 0.4% according to our table. It's here, isn't it? We don't have Martian earlobe syndrome, we've got a positive test. It's 0.4%. This all means that we can think of the probability of the positive of having a positive test as being the probability of getting a positive test if we do have Martian earlobe syndrome, plus the probability of getting a positive test if we don't have Martian earlobe syndrome, scaled by the chance of getting of either of those things happening. Let's whack that in. So here we go. It's a big one, isn't it? So the probability of a positive test equals the probability of a positive test, given that we've got Martian earlobe syndrome, times the probability that we've got Martian earlobe syndrome, plus probability of positive test, given that we haven't got Martian earlobe syndrome, times the probability that we've not got Martian earlobe syndrome. And seeing as we either have it or we don't have it, we can simplify that down to 0.95 times probability that we've got Martian earlobe syndrome plus 0.004 times 1 minus the probability that we've got Martian earlobe syndrome. So that 1 minus p mes is the same as probability we don't have Martian earlobe syndrome. Okay. If you need to spend a couple of minutes just thinking about that, please do. But all of that together means that we can express the probability of having Martian earlobe syndrome, given that we have a positive test, as a function of the baseline risk of us having MES. So that probability Martian earlobe syndrome. Let's just make that a thing. So here we go. Probability of having Martian earlobe syndrome given we've got a positive test. And you see the only bit of uncertainty in there is the probability that we have Martian earlobe syndrome. Now, to me, that just looks like an equation. I'm quite a visual person, so let's look at it like a graph. So this graph is just that equation done. This graph shows how the chance of us having Martian earlobe syndrome, given a positive test, which is what's on the y-axis there, changes as this baseline risk of us having Martian earlobe syndrome changes. You're probably looking at that thinking that the probability gets near to 1 pretty quickly. That's because, like most diagnostic tests, it's pretty good. If you think there's even a 10% chance that you've got Martian earlobe syndrome, which is sort of down here somewhere, the test is probably worth it, depending on the consequences of that testing. So if we're doing full decision analysis, we have to include the consequences of all our decisions before we weigh things up. If you think about it some more though, it will help you to understand the issues of general population testing for illnesses that have a low prevalence. Once the proportion of the population with an illness gets below about 4 in 1,000, in this example, the chance of a positive test actually meaning that that person is ill is below 50%. It's still a good test. It's just that there are so many more people who don't have the illness than have it. So conditional probability then can help us to understand why population screening may be problematic And it really drives a lot of the way that we use population screening, the reasons that we focus screening on high-risk individuals, the reasons that we use multiple screens once somebody has a positive test, and the reason that we only give results to people from qualified professionals, because sometimes they have to explain some of these complicated risks. What's even more powerful though is that this approach allows us to shift from frequentist probability to epistemic probability, which we're going to do now. So this is all about uncertainty, which I'm quite a fan of because it exists in the real world. Right, we're going to stick with the graph that I showed you before. Look at that PMES bit, so this x-axis. If you remember, that's the baseline risk of having Marshall earlobe syndrome, probability Marshall earlobe syndrome. We also have probability Marshall earlobe syndrome given a positive test, and we've seen how they're related, this nice red line here. This is all conditional probability, but it's also telling us how we should change our beliefs given more information. During the example I used right at the beginning of this session, I said that 2% of the population of Coventry had Marshall earlobe syndrome. Just to be clear, because this is the internet, this is made up. No one in Coventry has, to the best of my knowledge, Marshall earlobe syndrome. I've checked. If we know 2% of the population has Marshall earlobe syndrome, and we have no other relevant information, that PMES, that probability of Marshall earlobe syndrome, would be 2% or 0.02. We can stick that into our equation and it tells us this. So PMES given a positive test, right? We've whacked our 2% in as PMES, and it allows us to do a big sum, and that big sum gives us 0.83 or 83%. So if I'm living in Coventry and I know nothing else, a positive Marshall earlobe syndrome test should change my belief that I'm infected from about 2% to about 83%. That's pretty cool. We've updated our belief based on new evidence. Lo and behold, we've shifted from a simple view of statistics based on the relative frequency of things to a form of statistics that talks about degrees of belief. We're now in the realms of Bayesian statistics, which is a particular form of epistemic probability. So just to remind you, this is what we said about different types of probability before. We are now in the realms of judgment, this stuff on the right hand side. This is a powerful trick. Part of the reason that I've presented Bayesian statistics this way is because it's important to realise that chance and judgment are not separate views of probability, but the epistemic view of probability is a natural consequence of frequentist approaches. They're not in contradiction. I'm saying that because sometimes you'll come across people who describe themselves as Bayesian statisticians. What they mean is that they spend more time doing Bayesian analysis than other types of analysis. They aren't really at war with frequentist statisticians. They are just looking at a different branch of the same fundamental thing. Right, we haven't quite finished with Marshall earlobe syndrome. In the next section, I'll be talking about applications of these methods. To get a feeling for that, we're going to deal with an issue I mentioned ages ago. Uncertainty. The most important thing in statistics, and the bit that's often left out when you see it on the news or whatever, the most important thing is uncertainty. Statistics is the science of uncertainty. We are always uncertain. That's not a bad thing, it's just the way the world is. Bayesian approaches give us a way of handling uncertainty. Let's say I have absolutely no idea what my baseline risk is. At least I have my equations. Here they are. When we did this before, we put in a value for PMES. But we don't have to put just one single value in there. We can put in an entire distribution. If we have absolutely no idea what our baseline risk is, we can put in a flat value where everything between 0 and 1 is equally likely. Now if we did this using proper maths, it can get a bit tricky. So we usually cheat and just simulate the distribution. So let's do that now. To produce this graph, all I've done is use Excel. As a side note, never ever use Excel for proper Bayesian analysis. But I've used Excel to generate 10,000 pseudo-random numbers between 0 and 1. This gives us this prior distribution, this blue distribution, which is running along the bottom there. Then I've put each of those numbers through our Bayes equation, this one here, to calculate the posterior probability. This is the probability that we have MES given a positive test, so this value here. The distribution of the results of that is the red line here. You see it's low and then it shoots up here. What this demonstrates is that a positive test changes our belief about whether we have Marshall-Earlobe syndrome really strongly, even if we have no real belief to begin with. This is really cool because we have included uncertainty in our estimate. Now often when we're dealing with uncertainty, we sort of assume that it propagates. That is, we assume that if we're uncertain at the beginning of an analysis, we remain kind of unsure at the end. This demonstration is showing that when we have some evidence that's really strong, in this case a really good diagnostic test, the uncertainty we started with can be removed almost entirely. Now the example I've got here is carefully chosen. Medical testing is quite a simple situation, sort of. It has some subtleties as we've seen, but generally with medical testing we have a fairly good idea about the sensitivity and specificity of the test by the time we're looking at these sorts of things. And this means that the link between the evidence we see and the hypothesis is quite clear. Let's break that down some more. So here are the equations we had before, same ones. We're just going to concentrate on this top one for now. So the general case, the general Bayes theorem. In the graph, I referred to the PMES bit as the prior. This is because this is our belief distribution prior to the evidence being available. So before we knew anything. So let's mark that on the equation. So that's PA in this is the equivalent of PMES down here. The red line was the posterior. And this is what we calculated using the equation here. PMES given a positive test, or here PA given B. Here it goes. It's red because the line we used to mark it is red. Now you can see that we have two bits of the equation that remain in white. We have this bit here and this bit at the bottom. The first of these is referred to as the likelihood because it captures the likelihood of our data occurring if our hypothesis is true. This ties together the prior blue bit and the posterior, the red bit, and so I've made it orange. The final bit, this bit at the bottom, is the probability of the evidence under all the different hypotheses you have, and it's referred to as the marginal likelihood. It's in green. Now, apologies if those colours aren't easily distinguished for you. I hope the labels help at least. The likelihood and marginal likelihood are related. You can see this in the equation below, this one down here. Yep, because we've got that component, we've got that component, then we've got the counterfactual, you know, the opposite of it. Basically, they depend on the statistical model you're using to tie together the hypotheses and the data. Because we're using a medical testing example, that model's quite a simple one. If we were doing something like a network meta-regression or something like that, it'd be a lot more complicated. If we didn't know what the sensitivity and specificity of the test was precisely, we could add uncertainty inside our likelihood model, which would then be found in the marginal likelihood as well. You can actually do it pretty easily, but we'd need to simulate quite a lot more data to do it. And that's where some of the stuff that you'll come across if you see these types of analyses where people talk about chains mixing and things like that, that's where that comes in. It's the complexity of actually simulating it out to get a good solution to what are quite complicated equations. The ability to explicitly distinguish between uncertainty about our beliefs and uncertainty about the way we model the world is really important, because understanding what drives our uncertainty can help us make better decisions. So if we're comparing drug treatments, for example, if we have uncertainty caused by the we often have uncertainty caused by the lack of trial data, but we also have uncertainty caused by not necessarily understanding exactly how the drugs work, which is reflected in having slightly different statistical models. With a Bayesian approach, we can compare those sources of uncertainty. We can explicitly estimate the size of that uncertainty and then how that affects our decisions. And then we can use that to plan our research. So in medical drug development, we can use that to decide whether we need to do more trials, maybe bigger trials, or whether actually what we should focus on is more basic lab science to understand the similarities and differences between different treatments. That's really important because those decisions underpin an efficient drug development process. And we need a rational way of making those decisions. These are the reasons I like Bayesian approaches. I like statistical models with explanatory power. I like models that we can use to test ideas we have about the way the world works. But that's not all the statistical models in the world. That's not everything that we use stats models for. We're about to enter the related but very different world of data science and machine learning. Just briefly. So the sort of Bayesian analysis I do usually relies on simulating large amounts of data based on a statistical model and comparing the results to what we observe in the real world. That's neither fast nor efficient. It's just easier than doing all the calculus required to get a formal result out of a complex model with lots of uncertainty. In contrast, there are lots of statistical situations where absolute accuracy isn't as important, or where you need or want to make decisions rapidly, or where lots of data is coming in and you need to prioritize it on the fly. That's a classic data science problem. Bayes can help with this. It's not the only way, though. What I'm talking about here are things like classifiers. Specifically, the naive Bayesian classifier. Classifiers are statistical models that are used to learn features that predict classes for an event or object. They're often used in machine learning discussions because they're useful in automating the classification of large amounts of data based on training data sets. So, you know, on the example on the right there, you get loads and loads of relatively unstructured stuff coming in. You put it into a Bayesian classifier and then it takes all of that stuff and then puts it into, in this case, 3 classes. So examples of that, in systematic reviews, we might use a Bayesian classifier or a similar approach for filtering through literature lists and prioritizing articles that are most likely to be clinical trials, so we get a good idea of what the results are looking like as we're doing all the article sifting. Or we can apply that to data as things are being published, so we know when we need to update our review. In advertising, we might use this for sorting website visitors into groups based on their expected interests or purchase type, so that we can serve them tailored adverts. Obviously, most of the internet is about serving tailored adverts, and as you will have seen, quite often that's done very crudely. In criminal analysis, we might use this sort of approach to highlight offenders most at risk of reoffending, so that we can prioritise support after their release, concentrate those rehabilitation programs where they're most likely to have impact. The general sketch with classifiers, with Bayesian classifiers, is that we take a learning set, so a load of data where we've already classified things by hand, and then we apply, we use that to develop a model, to parameterize our model, to work out what the values in our equation here are. And then we apply the model to a new set of data. Typically what we'd do is we'd have a known set of data, we'd use one to develop the model, we'd use half of that set to develop the model, then the other half to test the model. For these models, the effort you're going to put into developing it will depend on how much time you have to develop the model, how important it is that the model's correct rather than just an indicator, and how computationally efficient you need the model to be. Often, naive Bayesian classifiers are used because they're easy to put together, quick to run. A lot of machine learning libraries for standard libraries for things like Python or whatever will include a naive Bayesian classifier. They can be quick to run, and they can be good enough as a first effort on a job. I think quite often you want to tweak them a little bit, spend a little bit of time optimizing them before you productionize them. Okay, that's just a taster of other uses for Bayesian methods. I don't want to talk about machine learning too much because that's a much larger issue. I don't want you to think that all machine learning is Bayesian, because it certainly isn't. So instead, let's recap what we have so far. So what we talked about today during this session, we talked about why Bayes matters, particularly talking about base rates and risk, and that denominator. Whenever we're talking about probability, we've got a denominator that we need to think about. But Bayes matters much more than just because of denominators. It matters because of uncertainty. We've got to an understanding of Bayes by going through frequentist statistics, particularly talking about probability, the multiplication and the addition laws, which we can understand using set theory, and they bring us naturally to conditional probability, which is the probability of one thing given something else. Then we've shown how that conditional probability leads to Bayesianism and a more sort of epistemic probability, where we update our beliefs as more data comes available. Then finally we talked about some of the uses for Bayesian approaches. That's all I want to talk to you about today. So I hope it's some use to you. If you are dealing with Bayesian analysis, I hope it helps you understand what people are talking about when they use terms like prior and posterior and marginal likelihood. I think the real message I want to bring out, though, is that it's important to embrace uncertainty and not hide from it. Things like Bayesian statistics are a really cool way of saying, yes, there is uncertainty, we're going to accept it, we're going to deal with it, and we're going to see if we can remove it by using evidence. And sometimes huge amounts of uncertainty can be dealt with quite efficiently because of good evidence. Thank you very much.